Good afternoon. My name is Ben Lauwens. I know it's very difficult to pronounce Lauwens, so I will do it for the presenter. So I'm an associate professor in applied mathematics from the Royal Military Academy. At the same time, I'm an army major. So it's a strange combination, but it exists. I'm here. And today I will have a talk, 30 minutes, about combining discrete event and continuous time simulations. So during military training, I've learned how to give a presentation, and one of the key points is to get the attention of the public. And you can do this with a quote. This is a quote from Einstein. Everything should be made as simple as possible, but no simpler. And that's really, really true for simulations, because you're making a model, you make something, an abstraction of reality, so you have to simplify. And you cannot simplify too much, otherwise you're not really modeling what you want to model. So I think it's something you have to keep in mind, because it's very, very important. Yeah, the contents for today. We will start with a riddle. Yeah, a lot of people here do it, but nobody agrees about what it is. Of course, this is modeling and simulation. Then a tale of things that happen in time. And tale, I know normally you have to write it differently, but this time it's the right, it's correct. Then we have a problem. There are spaghetti code everywhere. You have to get out of the spaghetti mess, and luckily for us, we are Julia programmers. We have some nice Julia comfort food. Then something that's quite logic. Not everything is discrete, but our computers are today. I don't know in the future. In the past, they were not discrete, they were analog. In the future, I don't know. Quantum computing, is it digital, is it analog? We'll see. And of course, we'll end with a kind of demonstration. The proof of the pudding is in the eating. In fact, it's a Spanish proverb from Cervantes. It had something to do with eggs and not with pudding, but we'll continue. So first of all, I'm a mathematics professor, so I have to start with some definitions. I think definitions are very important, otherwise you don't know what you're talking about. And the first definition is, what is a system? Because we will be modeling systems. A system is a set of connected things or parts forming a complex whole. So that's very, very broad. For example, a nice system is when this session ends, everybody will go outside and will have a cup of coffee. This is a system. We are part of the system. We'll get going out. We'll queuing up there. This is a system. We can model it. What is a mathematical model? Yeah, that's a set of hypotheses, data, inferences presented as a description of our system. Then, yeah, there are two types of models. The first one, an analytical model, it's simply a set of equations that characterizes the system. For example, yeah, you can have a predator-prey system, and it will be modeled by a system of differential equations. But we'll start speaking about simulation models. And simulation models are a little bit more delicate. It's a dynamic representation of a system that mimics the operating behavior of the system and contains its functional relationships. Oof, that's a tough one. Yeah, in fact, it's doing whatever is happening in the real world, doing it in a model, describing what happens. For example, when this session ends, we're leaving the room, we queue up for coffee, taking a cup, getting some coffee, sugar, milk, and giving way for the next person. Yeah, that's a model, a simulation model of the fact that we are going out and having a cup of coffee. Something that's very important about simulation and simulation models is time. Yeah, even if you're interested in steady state values, still time is a parameter, because we will see what's happening in time. So without time, we don't have any simulations. And the first thing we can do, and this is in fact what von Neumann and Ulam did for the Manhattan project to test the atomic bomb. Yeah, you can sample periodically the state of your system and to see, has something happened? And you note if you have kids, are we there yet? Are we there yet? That's really what's happening here. And on the drawing you see it very well. The red star is the interesting event that can happen. So we are sampling, we're not there yet, we're not there yet. At a certain moment, yeah, we are even too far because this event has already happened. And that's one of the problems we are seeing with this kind of simulation technique. Yeah, we are going over the correct value. And we have to going back to find the correct time. So one of the key points here is what's the granularity of your simulation to get the desired results. Luckily for us, we can do better. Doing better is doing it with discrete events, because every time we are looking, is something happening, is something happening? Yeah, we are not interested in the state of our system because it didn't change. So what we'll do now, we'll fast forward the time from now till the next event that's important. And what's happening in between, it is of no importance. This we can do in Julia, using the SimJulia package. First of all, we have to make a simulation world. I've called it an environment. I create an event. What's important about an event, we can add callbacks. A callback is simply a function that will be executed once the event is triggered. Then I schedule the event and I run my simulation. And what you see here, the function, the callback, is a very normal Julia function. The first parameter argument is always an event, and next we can give whatever we want. And it prints callback from event at time, now event. And what is the result? Callback from event 1 at time 1.0. Then in our callback, we will create another event. We'll wait for it, we schedule it. And the third event will be run at time 2.0. So my question for you is, where is the second event? Yeah, that's a good question, because we have event 1, event 2, event 3, where's the second event? Of course, I've programmed the end of the simulation, the run event 3 seconds. It's also an event I've created. So I'm eating my own food. Everything is event-based. Now, working with events is very nice. What do you need? A scheduler. I've implemented a binary heap. It's based on a priority queue. It's a very simple heaping structure, a very simple heap. Why this heap? Because we don't know anything about the order of all the events. And when we don't know anything about it, because every simulation can be different, take the most simple structure that exists, and that's a binary heap. It works very, very well. Then you have the event, can be scheduled, and callbacks can be added. And of course, we need an order. What's the order of the events? Scheduling time, priority, and event creation. Yeah, because we can have the same scheduling time, the same priority, then the events will be scheduled in order they are created. Yeah, and then we have a big problem, because if you program with events, and you can do it, I've programmed, I think, in a dozen programming languages, these kinds of simulators, even in Fortran and C++, Java, whatever. Yeah, you always end with spaghetti code, because all your events has to communicate together, and you have to make one big. It's in reality it's a big mess, because everything is related to each other, and you cannot structure it very well. For example, what I've done is an implementation of a radio protocol, because I'm a telecommunication engineer. It was very nice, it worked well, but at a certain moment I had to change something. It took even longer to change one thing than implementing the whole thing at the beginning. So that's something that's very important. Discrete event simulation without support from a programming language is really a hell. Luckily for us, tasks are simulation implementers' best friends. What's a task? A task is an implementation of a coroutine, and I know very well that not a lot of programmers know what our coroutines are, and so I'm citing the famous Professor Nutt. Stop thinking of one function as the caller and the other as the callee, and start thinking them as cooperating equals. So when we are speaking about coroutines, it's not one function that calls another. No, the function that calls and the function that's called. You don't make any distinction between both. So I've taken here the example that's also in the Julia documentation, a Fibonacci series based on tasks. So what's happening? We are creating a task based on fib, a simple function. This function will produce values, yeah, and the return will be consumed by the print that we have here. So what's happening in reality, your function fib, it starts running the first time. It goes till the produce. At that moment, the print consume will take over. It will print the value. And then the next time we do print consume, we will start after the produce and we will continue the loop. So what's happening here is something that's asynchronous. We will go always in the same function multiple times, and we can have multiple entries. Of course, it's very nice to do some simulations, because a simulation is nothing else as a state machine in disguise. Whatever simulation you are doing, it's about state machines. And what is a state machine? It's a model of computation based on a kind of hypothetical machine that can have one or more states, and only one single state can be active. So the machine must transition from one state to another to perform the different actions. So and in a simulation, it's always the same. How have I implemented this in Julia? I created a type process, yeah, that contains a process function that's wrapped into a task. And this function will describe the behavior of the simulated objects. And then I need a function to go out of this process function, and I do it with yield. Yields will say simply, okay, I've done here, I give the execution to another event, another process, and when a certain event is triggered, it's again my turn to continue running. And then we can do our simulation, our model that we had from leaving this room and go out to get a cup of coffee. We can implement it with this code. So I create my simulation, a process. The process is end of the afternoon presentation session. This is a simple function. The first argument is the environment. And what I do there is a yield timeout. So I say simply, okay, call me back when 100 minutes has passed. And then I'm creating another process, yeah, leaving the room. And what is leaving the room doing? At the start, it waits for the end of the other process. So we can couple process, and a process is also an event. So we are waiting there till 100 minutes has passed, and then it will take over. Then we create the coffee corner. It's a resource. We have to queue for it. Then I have some distributions, arrival distributions, service distributions. I will create the persons going out, this room going to the coffee corner. And of course, they are also processes. And then I have the process, the coffee lover that's created. What is he doing? He's, first of all, he prints out, okay, I'm going out of the room and I want some coffee. He asks the coffee corner, okay, can I have some coffee? Of course, perhaps there are people before him, so he has to wait. So there is a yield request, so he goes out of his scope and he will come back once he can take his coffee. He prints out, okay, I can have my coffee. Then there's a timeout, because taking the coffee takes some time. The timeout has passed, and then he will release the resource he owned, and another person can take the coffee. And what can we see here? End of the afternoon presentation after 100 minutes. The first one leaves the room. He can, of course, there's nobody before him. The second one leaves, he has to wait. The third one leaves, he has also to wait. The first one has a cup of coffee. The second one can also take his coffee. He can drink it, and so on. And the third one takes it. So that's a simulation of what's happening here. Now, what I've seen is that this kind of simulations are very nice, but you cannot do everything with it. Why? Because a lot of things are happening in continuous time. And I'm just speaking about the differential equations. A lot of things, for example, a military guy, the flight of an airplane or a bomb or so, whatever, yeah, you cannot do it with this kind of simulation, because interesting thing happens during the time of flight, because your trajectory is changing every time step. Yeah, and of course we can solve this with a Runge-Kutta integrator. It works quite well. But then we can ask ourselves, what happens when we want to trigger an event based on this continuous output? And that's not so easy because, yeah, imagine we want the zero crossing of a certain function g of x, vector x. So every time step of our Runge-Kutta integration, we have to evaluate this function. It can be costly. We need a dense output because we can go over our zero crossing and we have to come back to find the exact time. Also costs some time. We need a route finding algorithm, yeah, to find the exact crossing time. So that's very, very expensive. We have still some other issues. We can skip even the zero because we can have something like this, a parabola. We are looking here and we're simply passing it, and okay, the other time we have never crossed the zero, but in reality we have crossed the zero. And again, when you do a Runge-Kutta of a normal numerical integrator, all the components of the vector x are treated with the same accuracy. And also, that's not true in reality. For example, when you have 3 dimensions, sometimes the x and the y positions are less important than the z position. So you want to have different accuracies, and this has a big performance impact. Now we can transform this system of differential equations to a state machine. And of course, if we can transform it to a state machine, I can use everything I already programmed in my discrete event simulation to do the simulation. And it's in the 2000, Kaufman and Saliers published a paper about it. And we are solving not the previous equation, the time derivative of x equals a certain function of t and x. No, we'll be solving the time derivative of x equals a function of t and q. And q is specified by hysteresis. The reason why I won't go in detail, but we need it to make to have a precise result. And this delta q is called the quantum. So what's happening? You see the green line. The green line represents q. And every time the difference between the blue line, x and q, becomes too big, a delta q, yeah, we will force q to have the same value as x. And then we integrate simply the time derivative of x with respect to time, and we get simply x, and it's linear. This is in fact what they were doing, and we can extend it to higher order. So what are the nice properties of this method? The quantized state follows a piecewise constant path. The state variables are piecewise linear trajectories. Higher order, it will be linear and quadratic, and so on. The difference between both is never more than our delta q. So that's very nice for error control. And we can also make the delta q proportional to the magnitude of our state. So we have a relative error control. And even more important, each step we are doing is local to a certain component of x. So we don't have to look at all the different components, like a Runge-Kutta integrator will integrate every component of this vector. We don't need it. We can simply look at this one component and everything that's related to this component. And of course, when we have a nice behavior like this, we can trigger for discontinuities very easily. Because it's in there, we have a delta q. We can look, okay, when this delta q is passed, we have to do something. So how can we implement this? Yeah, we need an integrator, and the integrator simply integrates this equation. The time derivative of x equals a function of t and q, assuming that we know the trajectory of q, that is normally a polynomial. We need a quantizer. The quantizer gives q in function of x. We need zero crossings because we will trigger some events. And I need some structure that holds the complete model. Yeah, and I call it continuous. It contains a function f, its derivatives, together with a kind of structure information, because we need, okay, which component depends on which other components, so everything we need. So I've done it with a kind of incidence matrices. And the good thing about this is that different states are updated at different times. So that's very nice, because this means that, yeah, we only have to look at one state to do the update, and perhaps if another component stays the same, we don't have to do these updates, and we are getting a better performance. So the flowchart, I will quickly go over it. First of all, what we'll be doing is we are advancing the simulation time to t, so updating the Taylor series development of x. Also quantizes the new coefficients q of I. Also quantizes next time of change in q. Also continues which states derivatives depend on q of I. And then for each j, so that fj depends on q of I, we have to do the update. I will not go in detail, but you see here the update. And of course, at that time, we have also to ask again to recompute the next time of change for q of j. And then also for the zero crossings, we're doing the same thing. So we are asking for every j that g of j depends on q of I. Also continues the quantized state variables q of L other than q of I affect the expression of g of j, and update these values, evaluate it, and estimate the next event time at which g of j equals 0. And of course, at the end, it's a discrete event simulation. We'll go to the next event of all the events that we have created. As an example, I've implemented the Lotka-Volterra predator-prey model. So it's about two populations, prey and predators, in the same biotope, and of course the predators are eating the prey. And you can describe it with this system of differential equations. For the moment, yeah, how I've done this, the API is still in flux, but I'm creating a continuous object. It is based on an integrator with an explicit quantizer. I'm saying I have two variables, x1 and x2, and the order I will be using is 7 this time. I define my two variables, and the differential equations are simply given by strings, so it's quite easy. I have starting values, and then I have a kind of precision, and then I run the simulation. What do we get? Of course, we get this nice plots. If we run everything, the prey and the predator. And of course, I did some benchmarking. I compared it with the Runge-Kutta integration. Also in the same framework, because when you compare something, you have to use the same framework to do the comparison. And what do we see? I've given here the different orders of my methods, 2 till 9, and then Runge-Kutta dormant prince 4, 5. And what do we see? Order 2, yeah, we have a lot of updates in x1 and x2, 21 seconds, and so on. But what do we see? Order 6 is very nice. We have 592 updates in x1, 654 in x2. Takes 0.27 seconds. Compared to Runge-Kutta, it's almost the same. It's almost the same, and the integration procedure in reality is very, very easy. Yeah, and then you could say, okay, but Runge-Kutta is still better. Why are you using this other way of doing this integration? Two things are very important. This is a system of differential equations with only two equations. Yeah, you can imagine what will happen when you have 10,000 equations, and the relation between different components of this vector x, they are sparse, so not every component depends on all the other components. So you get a really gain in runtime. And in case you add one zero crossing, Yeah, simply one zero crossing. Looking at the value, for example, here that x1 equals x2. Yeah, the Runge-Kutta method stalls immediately. So it takes 10 times more when you do it when you have this zero crossing. And of course, with this quantized state system solver, you don't have any. You don't see even that you're looking for a discrete event that's happening at a certain moment. And that's very nice. That's why we're using this. I had some implementation issues, of course. Yeah. What are the implementation issues? Yeah, you have seen the API is still in flux. It was a nice conference. The jump presentation gave me some inspiration to do it better with macros, so I will be looking at this. But there are still some more important things. I have to calculate all the time derivatives, because when you look at the things I'm giving to this integration is simply the differential equations. For the rest, everything, I do the analysis and everything is calculated by Julia. And for the moment, I'm using calculus.gl and I'm doing a symbolic differentiation. I could use automatic differentiation techniques who will be faster, but I have one big problem. When you look at these equations, I have, for example, the third derivative with respect to the time of x depends on the time derivative of q, and also the second time derivative of q. That's already a problem because I cannot fit it in this automatic differentiation package because it's not ready for it. It cannot be used for it. So that's one thing I've seen in JuliaCon several times. Also for the next one, polynomials or Taylor series are also packages I could use. The problem is I'm evaluating all the derivatives at the same time. And this I can do with a kind of Horner scheme in a very efficient way, but it's not yet implemented. Why? Because it's really a rare case I'm using here. And the bottleneck in reality is the root finding algorithm, because I have to calculate each time the next event time. So I have to calculate from a polynomial of order whatever the first positive root. How is it done? Yeah, I calculate the companion matrix of this polynomial equation. I look for the eigenvalues. Yeah, this is also time expensive. So if there is a better algorithm simply to give me the first positive real root, but yeah, I'm out of luck here. No good algorithms exist. I've implemented some, but yeah, it's not very well. It turns out that they are not better than the companion matrix method. Conclusion, I think JuliaCon is for me and I think for everybody a big inspiration for further improvements. SimJulia is already used. Yeah? Manpower planning, medical disaster management, survivability of analysis of army vehicles, simulation-based optimization of autonomous underwater demining. A lot of projects are running for the moment. Yeah? A lot of people are working on it. I will release SimJulia once the API for continuous, the version 0.4, when the API for continuous models is stabilized. It's still in flux. I will also implement stiff quantized state solvers. Why? A lot of differential equations are stiff, meaning that in the time scale from one component is very different from another component, and you will always look at the smallest component. What's good here is that I can do it without inverting a matrix. If I can do this without inverting a big matrix, I'm gaining some time, and my stiff methods will have the same performance as my non-stiff methods. So I can always use a stiff method to do this integration. And then I'm ending. Don't forget the most important feature of simulation. It's a feature. Yeah. Because why it's a feature? Because I'm the simulator developer. I'm not responsible for your output. If you put garbage in, garbage out. It's something very important, but I'm not responsible for it. You're always welcome to contribute to the framework. I've already some ideas about agent-based simulations on top of a discrete event kernel, a GUI for simulations, because a lot of people want to use it, but are not happy with doing it programmatically. building a Simulink clone on top of this discrete event simulation framework. I think this is a very nice one for Julia. And I'm very interested if you have some innovative applications, and you're always welcome, and I'm always ready to find new collaborations. Thank you for your attention.
Thank you. Questions?
Yeah.
Can you be more precise about what the problem is with the automatic differentiation technique?
Yeah.
Because that's really...
Yeah. I will go. It's this one. Yeah. The problem is that when you're looking at these equations, yeah, I'm putting in the values of this hysteresis variables Q, and they are simply external to the differentiation. And I have to control them because I'm giving them like, as a kind of matrix structure. I'm giving them to the function to evaluate them. And I cannot do this with automatic differentiation techniques for the moment. Perhaps it's possible, but I have to rewrite everything inside to give me the correct way to give these inputs. So it's not a problem about the automatic differentiation. It's the way I'm introducing the different values to calculate the derivatives.
Can you show the slide?
Yeah, the hysteresis is simply, I'm not integrating, I'm not solving the equation as it is, but I'm solving an approximate equation. And this approximate equation, I don't introduce the values x, but the values q. Yeah. These values q are something external to our differentiation technique. And that's in fact a problem, because I think it can be done, but I have to look at the internals of automatic differentiation techniques and figure out how I can introduce my variables q in it.
So is it the case that you have to basically differentiate two different functions?
Yeah.
One plays the q and one plays
Yeah.
the x?
Yeah, that's it.
Wouldn't it be possible to have two functions that are differentiable as inputs?
Yeah. That's one of the things I can do, but even then, the actual state of the automatic differentiation packages don't allow me to do this.
Thank you again.
Okay, thank you. Perfecte timing. Okay, yeah, the mic, sorry. Too fast.
Thanks.
Do you mind if I mic you up? Yeah. It's just for the... Sure.
Is Julia here?